Okay, I think that's 60 seconds of banter. Let's kick this off. Welcome to Gridium's webinar on MERV-13 filter guidance. This is part of our continuing series on COVID and its implications for operations of the built environment. We've been talking to lots of our customers about different COVID-related issues, and especially in California, where sometimes we have wildfire issues, the issue of MERV enhancing the filtration characteristics continues to crop up and up. So I'm very excited for today's webinar to dive a little deeper with Barry. Barry, let me introduce you. For those on the call that don't know Barry, Barry has a long and storied career in building energy efficiency, over 40 years in the built environment. Started just down the road here for me at Stanford, Phi Beta Kappa degree in energy and environmental engineering, and has been with Servidyne, his company that I think most of you will recognize him from, since 1981, a principal since 2014. Barry has numerous accolades across Energy Star, LEED, ASHRAE, and has been a real leader in thinking about the built environment and energy efficiency in the built environment. And Barry, we're very welcoming to you and the Gridium community to share your thoughts on filtration, on COVID, and to engage with our community as they have questions for you. Welcome.
Great, thanks Tom for the over-the-top introduction.
I have to mention the Stanford because it's so close.
Well, it seems far away from me. It's over 40 years ago, so. Yeah. No, thanks a lot, and I also wanted to express my appreciation for you and Gridium inviting me to participate today. Looking forward to getting into this exciting topic of MERV-13 filters. So I'd like to welcome everybody and congratulate you on being in a very rare group of people who is at least slightly interested in filters. Maybe some of you are on today because you didn't have anything better to do, or maybe you were supposed to be changing filters right now and this seemed like a better option. But in any case, we're going to get into some background on MERV-13 filters in the context of the pandemic that we're in the midst of. So hopefully we'll have a few lighthearted parts of this in addition to the technical information. Yeah. So what I'm going to do, well, first of all, I guess a disclaimer. I am not a health expert. I have no medical background whatsoever. I'm not even a filter expert. I just have been around for a while. And I would say that my main source of knowledge over the past 40 years has been talking with building engineers all over the country. Yeah, I have an engineering degree, I have a PE license, but we all know how much that stuff is worth when you get into a real building. So I really attribute a lot of what I know at this point to the back and forth with building engineers who are running buildings and know the ins and outs of them. So anything that you disagree with in my presentation today, it's because some building engineer told me, and I'm just repeating what he or she said.
I love it. I love it.
So what we're going to do, I'm going to walk through a little bit of context. Where do filters, and specifically MERV-13 filters, fit into the whole pandemic situation? And then talk about the ASHRAE guidance specifically related to filters, and look at some of the challenges that buildings are facing in upgrading their filtration. And those are primarily kind of three top areas: the pressure drop associated with higher efficiency filters, the energy cost penalty that can accrue due to using the more restrictive filters, and the increased cost of buying those filters. And then we'll wrap it up just looking at recommendations for filter changes in this current period. But first, I wanted to start off with a little bit of a selective history of filtration. So a few fun facts that probably most of you don't know, I had no idea before I tried to find something humorous to start this presentation with. I looked back at what's some of the history of the filter industry. You can see on this slide on the left is a diagram of the first filter designed for a cigarette in 1936. And then in the upper right is a picture of a, well, it's supposed to give you the image of a nuclear power plant. But the purpose of that image is to make the point that HEPA filters were actually invented during the Manhattan Project when they were trying to figure out how to make an atomic bomb. But in the process, they also needed to figure out how to filter out radioactive particles in the air so people didn't breathe them in. So two kind of interesting historical trend lines of filter design, cigarette filters and the Manhattan Project. And there is one common element that brings them both together. You can see the bottom right of the slide. There's a pack of Kent cigarettes open there with the filter end of the cigarette, and then a kind of a close-up shot of that filter. And you see the blue stuff in there. Well, what do you think that blue stuff is? Tom?
I'm kind of scared to ask. It's mold, or I don't know, it's something horrible.
Well, yeah, you're going along the right lines. It's asbestos.
Oh, I was gonna guess that, but I was like, no, really?
Yeah, no, that stuff's called blue asbestos. It was used in Kent cigarette filters in the 1950s, which there are many lawsuits you can find online now about that. It was also used in the HEPA filters that were designed during the Manhattan Project. So few design developments along the way till we got to our filters today. Hopefully no more asbestos in them anyway. Okay, so on to from asbestos to COVID-19. Wanted to start off just reviewing how the transmission is occurring, or what is known about how transmission occurs, as a basic backdrop to getting into where filters fit into this whole picture. So this is a diagram from the World Health Organization. You can see that the sort of the main, the transmission mode moving from the person coughing from left to right, the droplets wind up getting into the other person's nose, mouth, or eyes directly. That's one way of transmission. Another way is they land on a surface, somebody touches the surface, and then their hand reaches their mouth, nose, or eyes, and they get it that way. The bottom part of that slide illustrates another known mechanism of transmission, which is fecal. Toilet flushing, aerosolized virus winds up getting to somebody that's affected that way. But the mode that we're most concerned with in terms of filtration is in the top upper right with the turquoise arrow. And that is when the droplets become smaller and become airborne and are aerosolized, smaller sizes, lighter weight, and therefore able to travel longer distances and stay in the air for longer periods of time. Now, I know, Tom, you're an aerosol denier, but so
I'm not a denier. I think my interpretation is that the statements around aerosol transmission are largely issued in an abundance of caution. There's very little evidence, and what evidence we do see is very high concentrations of very sick people, and coupled with finding RNA fragments, which is very different than finding it in return air.
Yeah, no, I would totally agree with that. I think the way ASHRAE puts it is that there's sufficient evidence to be concerned about it.
Yeah.
But a lot of the headlines that you see about HVAC transmission wind up, when you're getting right down to it, are an in-room air conditioning unit blowing air across a table where somebody's sitting and the person at the next table gets it. It's not like there's evidence that the virus got sucked into a return air plenum and then back out through the distribution ductwork and out to the building. So
exactly,
that is it's an important issue to keep in mind in terms of perspective on all this stuff.
Yeah, I think just a comment here. I mean, I think the reason that this is so hitting so many buildings is that a particular building engineer, 3 or 4 layers above that building engineer, someone has made the decision, hey, we're going to enhance our filtration. That's the message that we're going to bring to the space. And I think for a lot of engineers, they're like, well, what does this mean? And is it really going to do anything? That's what we're hearing.
Right. No, and I agree with that. I think, and we'll get into this in a few slides, but ASHRAE's main guidance is number 1, ventilation, number 2, filtration. So there is basis for people to be asking about filtration, and what a lot more people know what MERV is now than ever knew before.
Yeah. No, you thought it was like a character from the Jetsons.
Thought there would be a few background points in terms of the virus size, particle size, and distance travel that would be important, again, as background to get into the filtration question. So the size, how big is it? The virus itself, 0.125 microns, but it doesn't travel alone. So when it's in respiratory droplets, it's larger than 5 microns. And in terms of how far those droplets can travel, it's typically 3 to 6 feet, but it has been shown to be able to travel further than that if it's propelled either by loud shouting or singing or through air movement. In terms of how long the virus can survive in the air, there are a variety of studies. One that's often cited has said that 8 to 14 minutes. But then there's another that said 3 hours. So it's a little bit questionable what exactly the science is saying right now in terms of the virus longevity. So in looking at risk mitigation, a lot of times you look at a hierarchy, and this pyramid represents a typical hierarchy for figuring out how to mitigate risk. So at the bottom, at the base, you do the things that are going to hit the main risks, and then as you go up to the tip, you do things that will further mitigate risk, but aren't as critical as the things at the bottom. So if we look at the first bottom base of the pyramid, in terms of mitigating the risk of transmitting COVID-19, it's the basic things of source control. So screening people before they come into the building, distancing when they're in the building, physical barriers, face masks. Those are the primary measures based on what is known about how the virus is being transmitted. Second up in the pyramid, based on surface transmission, is hand hygiene and disinfecting surfaces. The third part of the pyramid is ventilation, keeping enough dilution going on so that outside air is coming in to flush the air in the building and diluting the amount of virus that might be resident in the air. Now, some might argue that ventilation is actually more fundamental than the hand hygiene and surface disinfection. So you could kind of flip-flop those at this point. Next up is filtration. And that's where we're going to be talking about today. But it's important to see where that is in this pyramid. It's not anywhere near the foundational part of it. If you've done the filtration and you want to go a step further up the pyramid, then you go to UVGI or portable HEPA filters. And this is usually where you've got vulnerable populations or high concentrations of people, and or a medical healthcare facility where you need to take further measures to mitigate the risk. And then finally, if you've done all of these things and your tenants are still demanding further action, there's actually plenty of other options out there that I put generously in the category of snake oil. There are many products out there that are claiming to be magic bullets, and provide that added edge above this entire risk mitigation hierarchy.
Yeah, I think that's I think most of our customers are getting, emails and calls about those constantly. But of course, your point is it's the stuff at it's the known stuff in the bottom up to filtration that, is going to get you 99% of what you need to have for a response.
Right, and I think actually you might even get to 99% before you get to filtration.
Yeah.
Okay, so let's start talking about the filtration itself. So what ASHRAE's guidance is first and foremost to improve the HVAC filtration to MERV-13 or the highest level achievable. In some of the ASHRAE documents, it's saying MERV-14 now would be desirable. And in comparison, MERV-8 is the current commercial minimum standard. So if you look at the table on the right of the slide, this is actually the table from ASHRAE standard 52.2, which is the test standard for filters. And it gives you the percentage particle size efficiency that the filter must meet in order to reach that MERV rating. So there's MERV ratings from 1 to 16, and they're measured in 3 different particle size ranges from 0.3 to 1, and then from 1 to 3, and 3 to 10. So you can see as you get down to the higher MERV levels, the percent efficiencies go up in each of those particle ranges. One other thing that's important to point out regarding ASHRAE guidance is that sealing the filters to minimize bypass air is also part of those guidelines, and that's a really important aspect in addition to the rating of the filter itself. Okay, great, thanks. Okay, so in this slide, what we're illustrating is how these different MERV levels relate to efficiency by particle size. So this was a theoretical modeling study that was done, and each of the colored lines on the graph represent a MERV level indicated with the numbers. So you can see at the top, the green curve is a MERV-16, and the particle size is on the horizontal axis going from left to right from very, very small particles up to 10 microns. So you can see that all the filters have sort of a weak point. Their lowest efficiency is in that middle range between about 0.2 microns and 0.3 or 0.4 microns. And that's because there are 2 modes in which particles get trapped in filters. Very, very small particles are trapped through diffusion, and the larger particles are trapped just by hitting the fibers in the filter. So if you look at the table on the right of the slide, here's a comparison for the micron size range of 0.3 to 1.0. A HEPA filter catches more than 99%. A MERV-14 catches 75%, and those MERV-14 is the lowest rating that is applicable to healthcare. MERV-13, which is the highest rating that is typically recommended for commercial buildings, captures 50% of those small size particles, and a MERV-8 is not rated at all in that size range.
And just to interrupt here, I mean, we actually don't know much about the aerosol, the so-called aerosolized particle size that is important. I mean, it's a huge range, right? Because we don't know.
That's a great point. And the thing is that I mean, the larger particle sizes are probably not going to make it back to the air handling unit. So it is the smaller sizes that we're concerned with. But really, there hasn't been much, if any, scientific study done on what is reaching back to the air handling unit or the water source heat pump or whatever's got the return air path going to it. and what's happening there. So that's why, you know, filters are a part of the risk mitigation, but they're catching things that are, you know, well along the way from how most people are now understood to be, you know, transmitting the disease.
Yeah, yeah.
One question we get quite a bit is, if you have two MERV-8 filters back to back, does that equal a MERV-13? Or we've gotten the question, if I have a MERV-6 and a MERV-10, is that a MERV-16? Unfortunately, it doesn't work that way. So, and Tom, I'm assuming you're hitting the
Exactly.
button?
Yeah.
Okay, cool. So the way this really works is that you have to look at what each filter is rated to do. So if a MERV-8 filter, let's say it catches 10% of the stuff coming through it, you've got 90% hitting the next MERV-8 filter, and that's only going to catch 10% of that 90%. So you wind up maybe catching 10% and then 9% or maybe 19% combined, which is more equivalent to about a MERV-11. So that's not necessarily through a scientific experiment, but that's sort of a logical way of trying to understand how does it work having a pre-filter and a final filter.
Yeah.
So let's talk for a minute about filter bypass. I think everyone at this point knows what an N95 mask is. But if you hit the button to the next part of this slide, you can see that it's very important that people wearing N95 masks pay attention to the fit of the mask. This is an illustration of a person wearing an N95 mask that is not fit properly, and there's a gap which basically defeats the whole purpose of the N95 mask. And then the next picture on this slide shows somebody wearing an N95 mask correctly, and I'm very glad that she is, because that's my daughter.
Yeah. With the face shield as well. Yeah, I mean, just the center one is both gapped and is doing nothing to protect anybody if you're the one that's sick, because it's got an exhale vent on it as well. So your daughter's the only correct example on this slide.
Yeah, there's no bias here.
Yeah.
Okay, so if we apply it, we go to the next slide. If we apply this logic to filters, you can see on the left, not a great situation with those filters. On the right, someone has taken the trouble to tape the gaps between the filters. And if you go to the punchline on this slide, you can see that that gap on the left doesn't look that significant, but an ASHRAE research study showed that a gap of even less than half an inch, which is not that big of a gap, can allow 20 to 25% of the air to bypass the filters, because obviously the pressure drop through the opening is a lot less than trying to go through the filter. And effectively what that does is, if you had a MERV-15 filter with less than half-inch gap between the filters, the net effect is it winds up at a MERV-8 level of overall filtration. So very important to deal with filter bypass, in addition to looking at the MERV rating of your filters. And just one other point in regard to this, when you do increase the MERV rating, if you go to a MERV-13 and you had a MERV-8 before, when the pressure drop increases, that just means it's even more important to make sure there are no gaps, because air is going to try to seek those gaps even more forcefully than it did when you had the lower pressure drop filters in place. If we go to the next slide, we're going to now kind of move into talking about all of the obstacles to moving up to a MERV-13 filter. So first of all, let's look for a minute at what are some typical pressure drops for different types of filters. And there's a wide variety of filters available for different sizes, different styles of filter, and different applications. But I just picked out a few that I thought would be helpful to illustrate. So the panel filter, which is similar to what's illustrated in the bottom left picture. This is your cheap standard filter. Some of them are MERV-8, most of them are less than MERV-8. One that I saw that was MERV-8 had an initial pressure drop of 0.2 inches. These pressure drops are generally rated at 500 feet per minute of air velocity, and a final recommended pressure drop of 0.5 inch, and that's the point at which the manufacturer is recommending that the filters be replaced. If you look at a pleated filter, those are commonly available as MERV-8. Again, this is a 2-inch pleated filter. Typically, initial pressure drop similar to the panel filter of 0.2 inches. But in this case, manufacturer recommended replacement pressure drop of 1 inch, which is quite a bit higher than the panel filter. Now, if you look at the same manufacturer's pleated MERV-13 filter, same size, it has a higher initial pressure drop, 0.3 inches, but the same final pressure drop recommendation of a 1 inch at replacement. And then finally, looking at a typical bag filter, 12-inch deep bags, MERV-13, this is going to be a higher initial pressure drop. The one that I was looking at was 0.45 inches. But again, final pressure drop recommended for replacement at 1 inch. So you can see that depending on what you're starting with, you may or may not have a significant impact in pressure drop change by going to MERV-13. So first point is find out what your filter pressure drop is currently, both the initial pressure drop as well as the pressure drop when it's dirty when you're replacing it. And then look at the MERV-13 filters that you're considering and see whether there actually is a significant bump or not. If we go to the next slide, second big question we get is how much extra energy is it going to cost to replace my MERV-8 filters with MERV-13 filters? So this is a back of the envelope calculation for a 200,000 square foot office building. And what we looked at was, this is an office building with central variable air volume air handling units. So when you put a MERV-13 filter in that has a higher pressure drop than the previous MERV-8 filter, what's going to happen if you're trying to maintain the same static pressure set point is that your VFD is going to speed up to be able to keep the same airflow to the system. And so you're going to have an increase in fan energy. We've used an average assumed pressure drop increase of 0.3 inches. So it's kind of a midpoint, looking at that previous slide where we were looking at, potentially a 0.5 inch differential between the final filter pressure drop that you would replace the filter at with a standard filter versus a MERV-13. So we used 0.3 inches as a good midpoint. And then we applied it to 3 different areas. Understood most of the people on this call are going to be on the West Coast, maybe some in Hawaii. So we used Seattle, LA, and Honolulu electric rates to look at what the cost impact would be of this additional fan energy. And you can see for this 200,000 square foot hypothetical office building, Seattle with its less expensive electricity, about $2,000 a year. LA, a little over $4,000. Honolulu, just over $6,000. And when you look at it on a per square foot basis, it's about a penny a square foot per year. Seattle, a little over 2 cents a square foot, and a little over 3 cents in Honolulu. So it is significant, but it's not the end of the world.
Yeah, it's very helpful. Yeah, I think that's one of the big costs. Those aren't, of course, the only costs. I mean, these filters are also expensive too, right?
Yeah, and that's a perfect segue to the next slide. So if we look at this next slide, again, we're sticking with the 200,000 square foot building. And in this case, I'm going to use two different scenarios. One is the office building with central VAV air handling units. And we're going to go from a MERV-11 bag filter to MERV-13 bag filter. The other case, we're going to look at the same size building with water source heat pumps going from panel filters up to MERV-13 pleated filters. So in the building with central VAV air handling units, we would have about 100 filters at the size of 24 by 24, and assuming they're 12-inch deep bags. There's about a $25 cost premium per filter. That means that's $2,500 additional material cost per filter change. And if you change those filters twice a year, you're talking about a $5,000 additional cost for filters, which winds up about 2.5 cents per square foot per year. Now, if you go over to the water source heat pump building, in this case, you've probably got about 250 filters, and I just used a typical 4-ton heat pump size. It has 18 by 20 by 1-inch filters. In this case, the premium cost per filter is about $8. So again, you're looking at around $2,000 of extra filter cost per filter change for the building. If you do that twice a year, that's $4,000, and that's about 2 cents per square foot per year. Now, what's not included in this analysis is the labor, whether it's outside labor or in-house labor. There's definitely, going to be a labor element, and where that could come in is if you wind up having to replace the filters more often than you did before. So that could be because they get filled up more quickly, or you can't handle the increased pressure drop to leave them in there until the end of the expected lifetime. So again, this is just some hypothetical examples just to kind of give a reality check picture on what kind of costs we're talking about. And I might just add one point back on the energy slide. So we used the example of the air handling units, variable air volume air handling units, where there is actually going to be an energy penalty for the fan energy. If you have water source heat pumps or constant volume fan coil units or package equipment that's constant volume, you're not going to see a fan energy penalty. You're going to see fan energy savings, but you'll also see reduced airflow. So that's a whole different equation, where your main concern is not going to be the fan energy increase. It's going to be, can you maintain enough airflow, or what do you have to do to get the airflow back to where it needed to be?
Well, and potentially, less cooling capacity on extreme weather days as well, right? I mean, if you're slightly under capacity, and that all the capacity calcs were built on MERV-6 or 8, and your constant volume, you might not have enough cooling, right?
Yeah, no, that's a great point. There's the cooling capacity, and then in the extreme case, there's also a question of making sure you have enough. If you have a DX system, have enough airflow over the coil to prevent freezing up the coil.
Yeah, important considerations.
Yeah, so there are a lot of considerations depending on the type of building and the type of air distribution equipment. So in this presentation, I just picked out a few examples, but obviously you need to look at first and foremost, what current filters you're using and what are their characteristics, what MERV-13 filters are available on the market, and how those may impact your systems, both in terms of pressure drop, airflow, and cost. And, as ASHRAE guidance states it, you want to use the highest MERV ratings possible or feasible. That in some cases that may mean you can't get to MERV-13, but if you can get to MERV-11 and you had a MERV-8 before, or you had a unrated panel filter before, then you're still incrementally improving the situation. So if we go to the next slide, this is sort of the final wrap up of the main content. I did want to point people's attention to what ASHRAE is saying about filter replacement. And this is in the ASHRAE guidance, overall COVID-19 guidance, where the introduction to this is that if there is concern that there may be virus present on the filters, then this guidance should be followed. And that includes wearing PPE, which would be a mask, eye protection, and gloves. You want to make sure that the replacement filters are going to be snug when you do the replacement. And according to ASHRAE, when feasible, you can disinfect the filters with a 10% bleach solution or another approved disinfectant. You should bag the filters before disposing of them, but they can be disposed of in regular trash. And then when you're done, you want to definitely immediately wash your hands or use an alcohol-based hand sanitizer. And then finally, in terms of some resources, I think the links here are going to be useful in terms of going more in depth into what we touched on today. First one is ASHRAE has an entire page on filtration and disinfection that goes through the guidance on MERV level filters, mechanical filters, as well as all kinds of other filtration technologies. There's also specific guidance on upgrading the filtration at the next reference, and there's some very detailed step-by-step examples of what process you could go through to determine what level of MERV filter you could put in your specific application. They do use a couple of specific examples, but you can take a look at that and apply them to your own systems. And then finally, the National Air Filtration Association has a document that has a lot of FAQs that are really helpful, very direct and straightforward answers to some of the main questions about filters and COVID-19. And then finally, if none of those resources are satisfactory, you can always email me. My email address is at the bottom. I'm happy to enter into any dialogue that folks want to in the aftermath.
Great, that's very generous of you. And of course, we'll distribute these slides, so there's no need to write down these links. Okay, let's get some questions rolling. There are already some in the question panel, but if you can type in your question, I will QB those across. First one is on wildfires. So the question is, what kind of if we have another episode of wildfires in California, what can we expect if we go to MERV-13? So I don't know if there's actually been any research on this, but presumably those filters are not going to last very long. But if your mental model is like, okay, here's what the filters look like in a wildfire, and you're moving from MERV-8 to MERV-13, what's the difference?
Right. Now that's a great question. If you go back to slide 10, that had the filter efficiency particle size chart. Wildfire, smoke from wildfires, I believe the particle size that's typically cited is 0.4 to 0.7 microns. That's usually what smoke from wildfires is coming in. Mm-hmm. And so when you look at this graphic in the 0.4 to 0.7 range, it's kind of the worst point of a lot of these filters. But if you go to MERV-13 in that range, or if you look at the rating, which is 0.3 to 1, which is kind of a little extended from the 0.4 to 0.7 on both ends, you can see MERV-13 is going to catch about half of it. MERV-8 is going to catch practically nothing. So it is going to be a market improvement, although it's not going to totally eliminate it.
Yeah. Okay. Very helpful. Okay. Question coming in here. I hesitate to put the snake oil chart up because someone will be angry, but the question is about bipolar ionization technology. And, if we're, we're hearing this from a lot of customers as well, but if we're in there messing with filters, what should we also be exploring this technology of ionization?
Well, I think the challenge with bipolar ionization is that the jury is still out. What ASHRAE says is that the studies that are published that have been done independently have shown a wide-ranging effectiveness from effective to not effective, and there is a lack of scientifically peer-reviewed research on that technology. So more research needs to be done. ASHRAE advises to look at manufacturers' data and claims critically, and I think that's a very important point. The other, I think, important perspective on that is, where is that in that pyramid? It's certainly way at the top point. I'm not going to say it's at the snake oil point, but it's definitely in that tip somewhere. So if you've done everything else in that pyramid perfectly, you probably don't need to worry about it. But also, I would never consider something like that before you've done everything else.
No, that makes a ton of sense. I have a question here on my own side of it is, in I think our earliest COVID webinar, I described it that as much as a building science problem, this was a marketing problem, in that it was up to each individual building to tell the story of what they had done for the unique needs of that building. How do you think people should talk about a filtration change if they choose to talk about it? And by talk about it, I mean to tenants and to occupants.
Right. No, that's a great question. I mean, and we've been asked by a lot of clients to address tenant questions on, overall HVAC issues related to, concerns about coming back into buildings. And what we always counsel is that you don't start by answering the question about HVAC. You start by putting the whole thing in perspective, reiterating that pyramid of risk mitigation, all of the measures that are being done in terms of source control, in terms of surface disinfection, and then you put the HVAC measures in that context. And then when you do that, again, I think ventilation is the primary HVAC measure to be, focused on, and then filtration after that. And I think anything that you can do to improve the efficiency of the filtration is worth mentioning, even if you can't get all the way to MERV-13.
Yeah.
Because it does show that you're diligently looking at your systems and what can possibly be done to take all prudent measures to mitigate the risk.
Yep. No, I agree. I agree with you. Okay. Last call for any questions. I don't see any coming in. Barry, thank you so much. This is super helpful. I think we're gonna wrap it there. Any closing thoughts for folks? Let me flash your email up here again if people want to contact you. But any closing thoughts?
I would just say that you know, and I'm sure many of folks on or have already done this, but I'm sure your filter reps will be good resources to provide information on your existing filters and options for upgrading. You know, that's a great resource to lean on. You may wind up needing to engage with your test and balance contractors if you really need to, you know, figure out what's going on with your systems and want to get a better on-the-ground sense of what's going to happen if you increase the pressure drop. But I think when you look at the economic impact, you know, if you are in a building where you're going to have a fan energy penalty and you're going to have increased filter replacement costs, you know, it's relatively minor in the big picture. And if you can increase filter efficiency, it's not only a benefit in the pandemic situation, but it also provides cleaner air in general, less particulates, and a better environment for the building occupants. So it's a good thing to do, you know, at any point.
Okay, great. We're going to wrap it there. Barry, thanks so much. And as a reminder, we'll send out the slides and the recording. Have a great day, everybody.
Thanks a lot.